How you doing? Thank you for tuning in to this here video presentation by Mr. Larry Whittington, or as he want to be known, Mr. Whit. Mr. Whittington's know all about mathematics, and that is why he founded the Fort Bend Tutorings. Today we're going to learn about word problems. Not the kind where you curse people out, but the mathematical kinds. The kind I don't be understanding at all. Alright, get your ink pen and your pencil ready. Take notes, because you finna learn from Mr. Whit.
Hello ladies and gentlemen, this is Mr. Whit with Fort Bend Tutoring, and today's tutorial is going to be about combined variation. So what is combined variation, you would say? Combined variation is when a variable depends on two or more other variables and varies directly with some of them and varies inversely with others. So if you've already checked out our direct variation and inverse variation videos, we're going to combine those two concepts into one variation problem. Yeah, that's what we're going to do. So based on our form here, y varies directly as x and inversely as z. So this is the setup that will help us solve our combined variation problems. And you should be aware that it's going to be k, that's going to be our constant of variation, or it's also called the constant of proportionality that we'll be solving for and using throughout these problems to solve for our combined variation. All right, well, let's get started. Problem number 1 coming up. Okay, in number 1 it says if a varies jointly as the square of b and the square of c and inversely as the cube of d, and a equals 18 when b equals 4, c equals 3, and d equals 2, they want us to write a variation equation relating a, b, c, and d, and also they want us to find a when b equals 9, c equals 4, and d equals 3. All right, well, that's pretty much a tall order, right? So we're going to start out by setting up our combined variation. So make sure that you refer back to the format that I gave you on the first page of our lesson today. Therefore, A is going to vary jointly, which means that we're going to be multiplying two variables together. The square of B, so we'll have your constant of variation, you'll have the square of B, and we'll be multiplying that times the square of C. So here I have c squared. All of this is going to be over, as it says it's going to be inversely as the cube of d. So we'll have d cubed. And this is what we have thus far. This is the setup of our combined variation equation. And yes, my b does look like a heart because I have a big heart. You should know. So what we'll use next is the given information in the problem to solve for our k, meaning our constant of variation here. So I'll be replacing the a, the b, the c, and the d values with the given information in the problem. We know that a is 18 when b is 4, so I'm going to have my constant of variation multiplying on 4 squared, and then c is equal to 3, so that'll be 3 squared. All of this is going to be divided by 2 raised to the third power because our variable d is cubed. Now that I have this, I'm going to simplify and solve for my constant of variation. So this gives us 18 equals, we know that 4 squared is 16. We know that 3 squared is 9. And this is going to be our variable k here for the constant of variation. That'll be divided by 8. What I'll do from here is I'll go ahead and simplify this, knowing that 8 goes into 16 twice, and then 2 times 9 will give us 18, right? So we can rewrite this as 18 equals 18k. Solving for k, we'll go ahead and divide both sides by 18. And from here, we'll able to cancel out those 18s on the right side. We know that 18 divided by 18 is 1. So our answer for k is 1. And that's your constant of variation. So I'm going to go ahead and circle this constant of variation so we can keep up with it. And we'll use this constant of variation to write our variation equation. Remember that your variation equation is complete when you're able to solve for your constant of variation and replace it. So your combined variation equation is a equals b squared times c squared divided by d cubed. And this is the answer to part A. Write a variation equation relating a, b, C, and D. Red box it. That's right. Put it in a red box. All right. And there it is. That's our answer to part A. Now let's check out part B. Part B wants us to find A when B equals 9, C equals 4, and D equals 3. So let's go ahead and replace those values and solve for A. So plugging in our values, we have 9 squared times 4 squared divided by 3 cubed. All right, I know that 9 squared is going to be 81. I know that 4 squared is 16. I also know that 3 cubed is 27. I prefer to simplify as much as possible before I multiply, so that's exactly what I'll be doing here. I realize that 27 will go into itself once and will go into 81 3 times. Now multiplying 3 times 16, we get 48 for our final answer, and this is our value of A. Red boxing it. That's right, putting a red box around my answer because it's right, and I'm happy about it. There you go. That's problem number 1, ladies and gentlemen. Problem number 1. Thank you. Next problem. In problem 2, we have if t varies jointly as p and the cube of v and inversely as the square of u, and t equals 24 when p equals 3 and v equals 2 and u equals 4. A, they want us to write the variation equation connecting t, p, v, and u. And part B asks us to find t when p equals 2, v equals 3, and u equals 36. So let's go ahead and set up our variation equation here. We know that t varies jointly as p and the cube of v. All right, so that's my numerator. And inversely as the square of u, which means that I'll have my denominator u squared. In order to solve for my constant of variation, I'll be replacing all the values with the given information from the problem to solve for my constant of variation. So I'll be rewriting t as 24 equals my constant of variation k times my value of p, which is 3, times my value of v, which is going to be 2, which is going to be cubed, all divided by, and my value of u is 4. So I have 4 squared here. From here, I'll be simplifying this by rewriting this as, let's go ahead and make some room. I have 24 equals k times 3 times 8 divided by 16. I'll be simplifying my right side by 8 because 8 will go into itself once. 8 goes into 16 twice. And then I'll be able to rewrite my equation as 24 equals 3k divided by 2. All right. From here, I'll be multiplying both sides by 2 to eliminate the fraction. So I have 2 times 24 equals 2 times 3k over 2. All right. Next, 2 times 24 gives us 48. On our right side, the 2's will cancel out, and I'll bring down 3k. Solving for k, I'll be dividing both sides by 3 using the division principle of equality. So 48 divided by 3 is 16, and we have our variable k now. That's right, our constant of variation. So I'm going to go ahead and circle this in green. That's right, green circling it. Yeah, I'm going to make that a new thing, green circling it. It doesn't have the same ring as red boxing it, but green circling it, it's coming, okay? It's coming. Maybe not today. Maybe not today, but it's going to come. It's coming soon. All right, let's go ahead and use this constant of variation to write our variation equation now. So we're using our setup, and we'll be able to write our variation equation once we replace this value of k with 16. So I'll be rewriting this as t equals 16 p v cubed divided by u squared. And here we have our variation equation, and I'm putting a red box around it. Red boxing it. And that completes part A. So for part B, they now want us to find t when p equals 2, v equals 3, and u equals 36. So let's check that out. So I have t equals 16 times my new p value, which is 2, times my v value, which is 3, and that's going to be cubed, all divided by my u value, which is 36, and we're going to square that. All right, so this is what I have thus far. All right, and we're trying to solve for t. So I'm going to simplify this as much as possible here. So simplifying this, we have t equals 16 times 2. I'm just going to take care of the exponents first. So 3 cubed is 27, divided by 36 squared is going to be a large number. So I'm going to do myself a favor and expand this and write as 36 times 36. All right. From here, I'll be simplifying as much as possible. I know that 2 goes into 36 18 times. I also know that 4 will go into 16 4 times, and 4 can go into this 36 9 times. From there, I know that 9 will go into itself once and will go into 27 3 times. I know that 3 goes into itself once, and then 3 goes into 18 6 times. And then I know that 4 and 6 can both be reduced by 2, so that I end up with a result of 2/3. And this is my answer. Yeah, this is my answer. I understand that this may have been a hot mess to you, but it was much better for me than multiplying 36 times 36. I'm just saying. I'd rather have done that. So I'm red boxing this. 2/3 is the result. Red boxing it. And that concludes problem number 2. All right. We have problem number 3 now. In problem number 3, it says if m varies as the square of p and inversely as the square of r, and m equals 4 when p equals 4 and r equals 2, write the appropriate equation relating m, p, and r. And part B wants us to find m when p equals 6 and r equals 5. So let's go ahead and set up our equation. We'll start with m varying directly as the square of p and inversely as the square of r. All right, so it looks just like this. This is my combined variation equation. That's the setup for it. We're going to then solve for our constant of variation by replacing the m, the p, and the r values with the information given in the problem. So I know that m equals 4 when p equals 4, and we'll square that, and then that's going to be divided by my value of r, which is 2 squared. All right, so my value of r is 2, and we square that based on our setup here. Simplifying this, we'll be solving for k. I have 4 equals 16k divided by 4. Well, we know that 4 will go into 16 4 times, right? So we end up now with 4 equals 4k. So rewriting our equation, we have 4 equals 4k, and now dividing both sides by 4, we know that k equals 1. K equals 1. All right, and here's that green circle that you've been waiting on. Green circling it. Yeah, it's going to catch on. I know you don't think it will, but it's going to catch on. All right, so now that we know that our constant of variation is 1, we can write our combined variation equation as m equals p squared divided by r squared. And this is our variation equation. Using our variation equation, we will be solving for m when p equals 6 and r equals 5. So plugging in my values, I know that p equals 6, so I have 6 squared divided by r squared when r equals 5. So I have 5 squared here. Simplifying this, we'll have m equals 36, and 5 squared is 25. So our result here is 36 25ths. And this is our answer for part B. That wasn't bad at all. Red box it. Red boxing it. Yeah. And that's problem number 3. Problem number 3 was not bad at all. All right. Let's go ahead and move on to problem number 4 now. All right. Problem number 4 is a doozy. And it has 5 parts for us to answer. And it says the load X that a beam supports varies jointly with its width W and the square of its length L, and inversely as its depth D. Say that 5 times. Part A wants us to write the equation of variation. So we're going to start with our setup here. We'll have X equals our constant of variation times the width W and the square of the length. So that's going to be L squared, all divided by the depth D. Since they didn't give us a standard to go by, this will be your variation equation for part A. Let's go ahead and red box it. Red boxing it. Part B states that a 200-pound weight hangs safely from the center of the beam with dimensions 5 feet long by 3 inches wide by 4 inches deep. Find the constant of variation if all dimensions are measured in feet. All right, so once we have this variation set up here, we're going to be able to find our constant of variation now using the information from part B. So according to the given information, our load is 200. We have our constant of variation. It will be multiplying with a width of 3 inches, which will be converted into feet because it said that all the dimensions are measured in feet. Since we are given a width of 3 inches, we'll convert that into feet. So 3 inches converted into feet is 1/4 of a foot. And this is going to be multiplied by the length squared. So we'll have 5 squared, like so. So 4 inches converted into feet is going to be 1/3. So this is what I have thus far. Rewriting our equation, I'll have 200 equals 75K divided by 4. Multiplying both sides by 4, we have 4 times 200 equals 4 times 75K divided by 4. Your 4's will cancel out. You'll have 800 equals 75K. Solving for K, will be dividing both sides by 75. And this now gives me, once I simplify this by 25, you'll find that K equals 32/3. And that's it. So we end up with 32/3 pounds per square feet. So that's going to be our constant of variation in its unit of measurement. Red boxing it. And no, that's not 16. That's the abbreviation for pounds. All right? American pounds. Knowing our constant of variation is 32/3, we can now rewrite our variation equation as x equals 32WL squared divided by 3D. So notice how I have my 32/3 here. The 32 will be in the numerator, the 3 can be in the denominator, and we'll end up with this version of the variation equation, our combined variation equation that we can use to solve any further problems. Solving part C, it says what size weight would hang safely from a beam with dimensions 5 feet long and 6 inches wide by 2 inches deep. All right, let's plug in those values. We'll have x equals, let's go ahead and put things in view here. Thank you. X equals 32. If the width is said to be 6 inches, that means that in feet, it's 1/2 times our length, which is 5 feet. So that's going to be 5 squared divided by 3 times our depth. So our depth here is 2 inches. So that's going to be 1/6. So that'll be 1/6 of a foot. Let's go ahead and calculate this. We'll start in the numerator by taking half of 32. That gives me 16. We'll end up with 16 times 25 divided by 1/2. That's simplifying the 3 and the 6 here, knowing that 3 goes into itself once and 3 goes into 6 twice. This is equivalent to 2 times 16 times 25. All right. Multiplying 2 times 16, you get 32, and 32 times 25 is 800 pounds. Red boxing it. All right. That's the answer. 800 pounds. Now, within this, you saw quite a few complex fractions. So if you need to brush up on your complex fractions, check out this video on complex fractions by me in FBT. Next, we have part D. All right, in part D, it says, what is the effect on the load the beam can support if the width is doubled and the depth is halved? So let's go ahead and check that out. We'll have x equals 32. It says that our width will be doubled, so we'll say 2w times our length, that's squared, all divided by, and we're to keep in mind that our depth is to be halved. 3 times 1/2 d, the depth. All right, which is now halved. 1/2 times the depth is half of the depth. We'll be able to simplify this by recognizing that the 32/3 is our constant of variation, right? So if we were to take the 2 and divide it by the 1/2, let's see what would happen here. We would have 2 times the reciprocal of 1/2, because we're dividing by 1/2, which is 2, times our 32WL squared divided by 3. So we can now show that we have 4 times our original amount. So when they ask what is the effect on the load the beam can support if the width is doubled and the depth is halved, we can show that the effect on the load is quadrupled. It's 4 times the original amount. Okay, we'll say that the load is quadrupled. Okay, That's our answer. Red box it. Red boxing it. And that's part D of problem number 4. Your final part is coming up, part E. Let's check that out. For part E, it says, what is the effect on the load the beam can support if the length is doubled? All right, let's see what happens there. So we want to double our length. So we'll rewrite it as x equals 32w times 2l squared divided by 3d. Rewriting this, we'll have x equals 32w times 4l squared. All of this is divided by 3d. Notice the difference between our original setup and what we have now is this number 4 in front of the L squared. So that means that the effect on the load the beam can support if the length is doubled is that it's being quadrupled. It's being multiplied by 4. So that's the answer. All right. Now, of course, you can rewrite this to make it look a little cuter. Yeah, you can write it a little cuter. Yeah, you can just say that this is 4 times your original amount here to show that it's being quadrupled, and therefore the load, all right, put it in view, put it in view, put it in view. We can say the load is quadrupled. Can I spell today? All right, there we go. The load is quadrupled, and that is the answer. Yeah, I hate that load too. I'm gonna fix this load. This load will be fixed. Fixing the load. There it is. Much better. The load is quadrupled. That is the answer to part E. Oh, so you know we got to red box it. Red boxing it. And that does it for this lesson on combined variation, and that completes our series on variation. We hope you enjoyed it. So, as always, please rate, comment, and subscribe. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Witt, and FBT Fort Bend Tutoring. Peace.
We're going to be learning about such things as linear, quadratics, system of equations, tables, mixtures, work, oh Lord, distance, interest, of which I don't have much, investment. This is my favorite one. I'm going to name my grandbaby consecutive integers, algebraic translations, and percents. I understand a little bit about cents. I know that 50% off is pretty good.
I'm not scared of you. I'm not afraid of you. There we go. See, I'm just showing that I know what 3 times 5 is. And then 15 times 2 is 30, which is the answer to part B. I'm going to put a red box around it. I have to.